Okay, guys. Today we are going to discuss about the in foundation in automated technology. I'm actually going to discuss about this engine management system. So this is your session 2 for uh, in unit 4. So today what we are going to discuss is everything, right? You need everything that you have learned previously to actually be able to understand all of these things available here. Right, so we'll start with understanding. So what we discuss first, we'll discuss what are we going to discuss, what are we going to learn here. So first thing is what is engine management, and next we move into the closed loop engine control and engine control unit and engine mapping and computer vehicle control. So there's additional parts and full diagnostic and maintenance of the engine management system. So these are the areas we're going to cover. So this is how usually the control system. Today what we're going to discuss is how the whole control system of the engine actually works and how it's actually going to be linked with the fully complete vehicle control system. That's what we're going to discuss. So you have to understand now, as you might know that what do you call this? Um, what vehicles is autonomous vehicles are coming up. So the first step of the autonomous vehicle is controlling the whole engine and drivetrain and everything by a computer system. So we're going to discuss about that basic step or the first step of this autonomous vehicle control system or autonomous vehicle. So the base of the autonomous vehicles is the powertrain control module. So how the powertrain is actually managed. So the starting of the powertrain actually powertrain control is actually began with the engine management, right? So what is engine management? So so engine management is the control system that maintains and control every aspect of the engine. So engine will be able to perform at its best, right? So engine will be able to perform at its best. So very good example. I'll give you a simple example. For example, you might actually have this experience. So early morning, once you start the engine, right? Early morning, if you start in a engine, you might notice that engine is actually so idle. For example, the idle RPM may be around 800, 790 or something like that. But the vehicle, once you started in the early morning, engine is actually operating at a higher RPM, like 1200, 1300 RPM. The reason for that is to bring the engine up to the operating temperature as soon as possible, right? To bring the engine's operational temperature or engine's working temperature up to the optimum temperature as soon as possible. So this is done by this complete vehicle management system. So it actually, so by doing that, right, by doing that, engine will be able to work effectively later on. So otherwise what happens is, if the engine is not come up to the temperature, until the engine comes up to temperature, right, what actually happens is engine will not actually perform well. So your fuel consumption will be lower, and your fuel consumption will be actually higher, not lower. Fuel consumption will be higher. You will be feeling roughness in the engine. So all these issues will go away once the engine come up to the operating temperature. So bringing the vehicle into operating temperature, or bringing the vehicle or maintaining the vehicle at optimum conditions, is what done by the engine management system. So engine management system actually communicate or talk and look after everything related to the engine. So that includes the temperature, air, how much of air going inside the fuel, ignition, oil temperature, everything is actually being considered in here. But there could be some differences from engine to engine. Yeah, so for example, like normal usual day-to-day driving Japanese passenger vehicles may not actually have the engine oil temperature sensor, so something like that. But high-end vehicles might actually have these things. There are small differences between these things, but that's mainly due to commercial point or the financial point of view. So because if you add one sensor, means you actually have to add wiring, and the control system actually have to consider all of these things, and the programming is going to be larger part. So that actually going to add, like, if we consider that's only going to add like 100, or we say that whole addition of one sensor would cost like 50,000 rupees or something. But 50,000 rupees is, once you multiply it by the number of vehicles they manufacture, it's a big cost. So by sometimes some sensors may not be present because they are not absolutely necessary, right? They are not absolutely necessary, but if it is absolutely necessary, it will be always there. For example, oil pressure signal, so that's necessary. So without that, engine will not actually work properly. So that sort of that sort of communication and management is actually done by the whole engine. That's not all, actually. Everything, I mean, includes, like, for example, once you turn on the air conditioning, engine is actually getting additional load on itself, so it always have to overcome it, right? In addition to that, engine has to develop a little bit more power in order to maintain all the electrical components that are operating, for example, headlights and everything. So in such cases, engine actually have to change its normal idle control, idle temperatures, or not idle temperature, idle RPMs and everything. So all these things actually managed by or looked after by the engine management system. So engine management system is not exactly as we discussed earlier, currently vehicles are actually working in this closed loop control system, right? Currently the vehicles are actually working on this current closed loop control system. But it does not mean that engines management system is always working at closed loop control system, right? I'll explain this a bit later as well. In some instances, the control system of the vehicle actually work as a open loop system as well, but most of the time it's actually working as a closed loop control system. For example, if you turn on, or if you start the vehicle early morning, at that time vehicle is actually working as a open loop system for some time. Then only once the engine come up to like operating temperature, only vehicle will turn into a vehicle management system, will actually work as a closed loop control system. So we discuss about the closed loop control system. We know how the closed loop control system works in the injection or fuel injection system, as well as the ignition system. So we discussed this part, right? So basically, what actually happens in the management system, like operational wise, in addition, except for these bringing the engine up to the temperature and everything, what actually happens is taking account the sorry. So what actually happens is in the engine management system actually takes account all the mechanical conditions of the vehicle and properly make it run. So the driver will not be having any difficulty of driving it. So it will be very smooth once you have this fuel injection system. So uh, how it does is mainly it actually considers about the knocking of the engine, so it won't let the engine to knock. So if there's any tendency to knock, the engine will actually, tendency means if it is actually started knocking, the engine will automatically change the ignition timing in order to reduce the in order to avoid knocking in the next cycle. So for this knocking and all these sort of small changes happening inside the engine, there's so many things actually. It actually depends on so many things: compression ratio, octane number of fuels, volumetric efficiency, what sort of engine load is there, what sort of combustion chamber is there, airfoil ratio, engine temperature, and carbon deposits, So all of these things has to be actually included in the engine management system. There's no way for all these things to be measured by engine management system. There's some things it can actually measure, but it only uses the closed loop signal. Right? Closed loop signal means in the fuel system, it's actually uses the signal from the lambda sensor or exhaust gas oxygen sensor to identify how much of oxygen is available. If there's too much oxygen, that means too much hydrocarbon should be available there. So and at that time the fuel will actually reduce, or fuel will trim. We call it as fuel trim. So the amount of fuel goes injected into the engine will be reduced. And once you do that, if the engine started to knock, at such cases the ignition system understand that knocking has occurred by the use of the knock sensors, and it actually changes the ignition timing. So that means there are two feedback signals taken mainly. Well, first one is oxygen sensor. The second one is actually the knock sensor. So knock sensor is mainly used for the ignition timing. Fuel system actually use the oxygen sensor for its feedback signal. So even though we discuss about these things as two separate systems, right? Even though these two are two different systems, both of these are actually working together, right? Both of these are actually working together. So there are two different or two distinctive sections dedicated for actually finding out the fuel, how much of fuel has to be given, and what sort of ignition the advance has to be kept, or what is the amount of ignition advance has to be maintained. But all these things actually work together, right? All these things actually works together. So it's actually a combined ignition and fuel supply system. One thing you all have to understand is both of these systems actually utilize the same sensor modules. Both of these ignition modules actually use the same sensor module. So ignition unit and the fuel system or fuel control module, both are actually inside the engine control unit, right? So engine control unit is a small computer. Inside of that computer, there are small separate units that takes care of the ignition, takes care of the fuel, right? But it does not mean that these are completely they are not in contact with each other. They are actually communicating as well. They are communicating as well in order to maintain the engine's performance at best level. I'll go to the same place. I'll explain how these things are actually communicating with each one later on. So in order for since both of these units actually use the same sensors, there's no point of actually having two sensors for each. I mean, two sensors for the same measurement. So they utilize the same sensor and same output from each sensor to actually find out what are the ignition angles and fuel, how much of fuel has to be delivered into the engines. So this whole combination of ignition and fuel supply system is actually what is the basis of the engine management system. So we'll start with the fuel control system. I think we already discussed about this, so I'm not going to go through like so much details. So if you can remember again, so exhaust gas is actually coming out. The exhaust gas then passes around the lambda sensor or exhaust gas oxygen sensor, where it measures how much of oxygen. It's actually consider how much of oxygen available in the exhaust gas as a ratio comparing to the atmospheric pressure air and atmospheric air or oxygen content in the atmosphere and the oxygen content in the exhaust gas. Based on that, it provides a signal to the ECU. That's actually our feedback signal. So feedback signal comes into the ECU, and based on that ECU decided whether the fuel has to be actually increased or reduces. Fuel has to be increased or reduces. So but it does not actually give like a digital signal. It's actually the voltage based on how much of oxygen available in the exhaust gas. It's actually um, the voltage actually change from like 0.4 or 400 millivolts to around 800 millivolts. So it's our main, so the system is actually try to maintain around 400 450 millivolts, and it's uh, always try to maintain the air fuel ratio around 1. That means around here lambda around 1, while keeping the uh, while no- while so when this happening, sorry, yeah, so once around 1, right, around 1. So when during that area while it's trying to maintain the oxygen level around 1, it's always try to wait, so always try to maintain the voltage outlet around this area, right, voltage around outlet around this area, right. So it may not be possible, but try to maintain around this area near to 400 millivolt is the best level, but it's somewhat difficult. So this when the fuel is actually when the oxygen level is lower, at that time fuel is actually increased. Once the fuel increase, then oxygen amount of oxygen available gets lower. At that time engine again cut down the fuel. Then at that time engine started to go lean. Once it goes over a certain limit around 400 millivolts, then what actually happens is fuel system again increase the fuel. So then again it's actually increase up to the reach. So this cycle actually going to continue as long as the engine is actually running. This cycle is going to continue. So this is happening in a very fast manner, right? So once you actually if you try to grow it in a like a larger scale, it's actually something like this. Very small ripples are going to come, right? You can't actually see this. So this is like a exploded or enlarged. It's not exactly like this once you put it against actual working order, right? So anyway, it's actually going rich and lower, and maintaining it at the trying to maintaining it at the best possible level in order to maintain the air fuel ratio around 1, right, around 1. But while this is actually going on, the when air fuel ratio is changing, based on the air fuel ratio, as we discussed earlier, ignition also has to be changed, right? Ignition also have to be changed. So at that time, ignition system, while the fuel system is working on this, ignition system is actually working on maintaining the ignition timing at the sustainable level. So engine will not actually create a knocking, right? Engine will not create a knocking. So as I told you earlier, as I told you earlier, there are some instances engine actually works as a, or the engine management system actually works as an open loop control system. So the instant that actually works as a main instant the engine actually works as a open loop control system is when engine started in the early mornings, like cold start. So during the cold start, oxygen sensor is not actually up to the temperature. Oxygen sensor is not up to the temperature for to it to deliver correct readings. So it actually have to come up to around 573 kelvins. That's a lot of heat. So in order, that means around 200 something, around 200 centigrade. The engine exhaust has to, the sensor has to come up to around 200 centigrades in order to actually deliver proper readings, right? Proper reading. So to fix these, the simple system, what the simple system adapted by the manufacturers is to run the engine as a uh, open loop control system, run the engine management system, keep the engine management system as a open loop control system for some time, right? Until the engine come up to like operating temperature, it runs as a open loop control system. One disadvantage of, well, there's a lot of disadvantages. The main disadvantage, since the engine is as running as an open loop system, engine do not have any idea, it's not getting any feedback from the signal. So to maintain engine running properly, the engine actually have to dump a little bit of more fuel into the system to make it richer and not let it to turn off or stall, to avoid stalling. So as a result of that, engines actually heavily smoke at cold morning starts, right? Cold morning starts. But once the engine started to come up to the temperature, and once the engine started to get feedback, so once the engine turned into a closed loop control system, at that time engine started to uh, cut down the fuel, or then the engine will actually trim the fuel supply and maintain very good combustion, very good combustion. So the smoke will also store reduce, the smoke that's actually coming out of the engine will actually reduce. So um, uh, in some cases, some other examples is sometimes in very high accelerations and deaccelerations also, engine started to or the system started to go beyond the exhaust gas or exhaust gas oxygen sensors limit. At that time also, sometimes engine could actually give any could give like a trouble code in, if it is like a vehicle with trouble codes or check engine light. So in such cases, switching off and switching on the engine will bring it back to the normal conditions. So yeah, so yes, yes. Yes, yeah. So while this is actually happening now, the fuel system, while the fuel system is working on that, we have to actually look at the ignition system, which is working parallel to the fuel system in order to maintain the combustion process is going on. So as we discussed in the previous modules, how much of the load the vehicle speed is actually dictate the how much of ignition advance and retard has to be done for the engine. So that particular ignition point is actually dictated by what is the engine speed and the engine load. So while the fuel system is doing all these things, or all these fuel trimming, increasing or decreasing the fuel supply, that may that may cause for a knock, engine knock, because of uh, fuel starvation. And also, to make sure the engine is not going to knock, the ignition unit always measure the signal from the knock sensor. If there's any case or any if it was found there's any possibility of knocking, the engine will automatically, the ignition system automatically decrease the crankshaft or retard, or decrease the ignition timing by 1.5 degrees per once, until it's actually reduced, or until it's turn off the knocking. So as we can discuss in the previous uh, as we discussed in the previous module, so here it's actually showing a coil on plug type ignition system. as since this engine actually has a separate coil per each cylinder, it's possible for actually to make these changes separately from each cylinder. So for example, if the knocking started at third cylinder, it's possible to turn it's actually possible to switch fix the or take the corrective measures by fourth cylinder, because the signal is coming separately. You don't have to actually wait for some time to make this work again. So so as we discussed in the previous module, this spark advance, right, ignition time, this spark advance ignition timing is a very important, right, very important thing. So how much how much time necessary for combustion, the flame development phase, flame fast burning phase, and completion phase. So this whole process has to be completely done or completely finished in order to uh, complete the combustion fully, right? So to provide the necessary time, the ignition time actually has to advance or retard. So usually, as I told you, the maximum pressure inside the combustion chamber should reach between like 10 to 15 degrees from the from after TDC, right? 10 to 15 degrees after TDC. So in order to meet this particular time, this spark time and the complete burning time, right, or this fast burning phase is very important. So when the vehicle's speed actually increasing, when the vehicle's speed is actually increasing, the time available for this yeah, so when the time necessary the time necessary to complete this combustion is not going to reduce. So at that time the ignition have to start bit more earlier. So in here it says that the ignition started 30 degrees earlier, but if ignition given 30 degrees early, but if it is, so let's assume this is 1000 rpm. So if the engine is rotating operating at 1500 rpm, probably ignition may have to give around 32 degrees, 33 degrees early, right? So that time has to be actually changed. So even though the engine speed increases, the combustion time is going to be the same. So in order to maintain this this point C at the same level, the engine actually have to bring the spark ignition or the spark point bit earlier from the TDC point, right? The same thing happens with the load. So once you increase the load, at that time the amount of air goes inside increases. So at that time, amount of air going inside increases, the amount of fuel goes inside increases, right? So as a result of that, the fuel is actually burning faster. So at that time, what actually happened, this actually have to come bit back, right? It has to come a little bit back. So that means the ignition actually has to be reduced, right? Ignition has to be reduced because it's burning faster, right? It's burning faster. So this details also has to be fed into the system. Next one is air fuel ratio. So how much of fuel is actually inside the engine? So if there's too much fuel, then it's if it is actually rich mixer means again faster combustion, right? Again faster combustion. If it is a longer mix, if it is a weaker mixture, that means it's going to take some time for the combustion. So at that time ignition has to be advanced. If it is a rich mixer, ignition can be actually retarded. So these sort of things actually has to be done by the ignition system with the help of the signals or the data from the uh, other sensors, right? Other sensors means the speed, load, and everything. In addition to that, the readings or the airfoil ratio data, how much of fuel is injected into the engine from the fuel system. So that is where actually this fuel system and ignition system actually going to communicate, right? This is where it's actually going to communicate, but it does not mean that they're going to communicate directly. They're not going to communicate directly. There's a system actually involved in this. That particular system actually maintains this that particular system, I mean the engine management system, actually take care of the communicating part. So while this combustion and everything is happening, next problem is uh, emission, right? Emission. So when you increase the emission, right, when you increase the advance, there's a more possibility of emission. So higher emission possibilities there when you're increasing the uh, ignition timing, or that means advancing the ignition timing. So these have to be maintained in a very good level. So it's it's like this graph just showing a basic diagram. So what you have to understand is when you change one single setting, like changing the ignition advance, that's going to affect the so many other parameters, the engine torque, how much of fuel consumption was, the emission, everything actually going to change. So there's too much details, actually too much of data has to be considered. There's a lot of data has to be completed or considered in order to actually provide the necessary or provide or maintain the engine at optimum level, right? So this actually shows a basic system layout of ignition control module. So engine, while the engine is operating, we'll start from the engine. Wait. So while the engine is operating, and assume that if it actually found out there's a knocking. So once that actually found out, the knock sensor detects that, right? Detects that, and it's actually send it through some electronic system, small electronic system. I'm not actually going to go through all the details here because it will take so much time. It will take so much time. So basically what actually happens here is, so the knock sensor data will be actually filtered and identified which parts, which vibration signals or which voltages are actually related to the engine knocking. Then it's actually sent through a set of electronics in order for sending it to the in order for sending it to the control module of the system. So it will be able to actually identify which cylinder actually knocked. So once he found which cylinder is not actually, then it's send it through another two decision taking. Two decisions are taken, then it's compare the previous uh, strokes and previously recorded knock values and the one you actually received now, then compare them, right? Then compare them. Once comparison, this is where the decision is actually taken place. So once the decision was identified that this mean value and this actual value are similar, at that time there's nothing to be done, right? It's nothing to be done, there's nothing to be worried about. If it is something to be worried about, the ignition has to be actually retarded by 1.5 degrees, right? So that means yes. So then retard the ignition by 1.5 degrees, it's sent to the ignition control module, right? Ignition control module, then ignition control module actually send it as a ignition control module actually controls the ignition or retard the ignition based on the signal from there, right? So this is how the basic outline, right? This is just a basic outline. There's so much things actually happening here also which I didn't actually explain at this stage, and with the available time it's not possible to actually go through all of these things, but I guess you got a basic idea how the ignition system works, similar to how the fuel system actually works. So knock sensor in this case actually act similar to the oxygen sensor in the fuel system, right? So engine is always try to advance the ignition system, but once it advance, right? If it measured a knock output, then again, at that time, my engine understand, okay, there's knocking happening because of the previous advancement of the ignition timing. So now it's time to actually retard the ignition timing back. So that's how the system actually works, right? That's how the system actually work. But it does so all of these things, actually the fuel system and ignition system actually done in a small computer control module, right? Computer control module. So this is what actually happens in the computer control module. Means it's like a small, sort of like a small 8-bit or 16-bit computer, right? We usually use like 64-bit computers in our home, but vehicles use like 18 to 16-bit computers, because that's more than enough for the task in hand for a vehicle. So in vehicles, uh, one thing you have to understand is that in vehicles, they are not actually designed to do the calculations and find out how much of fuels. For example, if we consider fuel, it's not designed to actually identify uh, how much of fuel has to be delivered based on how much of air is coming into the engine. It's not like that, right? This particular ignition control module, or sorry, this particular engine control module or control module, control engine control unit, what actually it does is it's has a memory. It actually has a memory where it's actually stores every possible scenario for uh, the engine operation. So for every engine operational conditions, every possible scenario is stored here, right? So engine just use those data and implement or do the action, necessary action based on that. That's what the engine control unit does, right? So it's take the inputs from all the sensors, right? Then find out the then identifies this parameters or situation at that particular action for that particular situation at that particular time, and find out the corrective action and implement. That's all this part is actually doing. So the one main reason for doing that is, if you wanted to actually have a like a calculation, that calculation is going to take a bit more time. For example, it takes like twice the time as a this method, or this just reading the necessary action is only taking around 50 milliseconds. But if you do the whole calculation, it will take around 100 milliseconds, right? It will take 100 milliseconds. Not to mention the whole complexity of the control module or the control system, sorry, the engine control unit is going to be higher. So the cost of manufacturing is going to be higher, maintenance cost and everything is going to be higher. So for to be more financially viable, engine can actually just using this method is more useful. And since engines are just to designed to just run on a set of possible scenarios, there's no actual use for them to be. So there's no possible reason for actually them to be having the calculative capabilities and everything. But nowadays, it little by little starting to do the calculations as well. I'll give you some explains later. So one example is, yeah. So this data storage, right? Data storage is done in several ways, but one simple or one most popular method is lookup tables. I think you already know what's a lookup table in your foundational computing or computing technology or some module is there. So lookup table is where you actually store the data. For example, this is one example I actually found from internet. So there might be some errors, but I didn't find any errors at the moment. So this is just a simplified example how the lookup table actually works. So how it actually works is, so for example, in this case, this is actually so in this particular application, what actually happens is engine is rotating at 1920 rpm. So engine is operating at 1920 rpm. So engine speed sensor. So now engine is, when the engine is actually operating at this particular rpm, there should be a certain amount of ignition advance has to be done, right? Ignition advance has to be put on. So that particular ignition advance has to be found out from some. So how this actually does is, the speed sensor reads this value and it send it to a AC/DC converter. The computer system or the computer control or electro engine control unit is actually a digital computer. So it's only read it as binary values. So whatever the readings actually comes here has to be turned into a digital value or binary value. So once it's read as binary value, then the engine control unit actually looks into its lookup tables, right? It looks up to its lookup tables and find out the similar value. So in this case, this is the value and the similar value is here, right? So once you found the similar value, it's actually send it to a set of instructions, right? Set of instructions. So instructions in this case is the timing angle code, how much of ignition timing advance has to be put. So this is again a digital signal which turned into a decimal value or electrical signal, how much of advance has to be put into the sent into the ignition control unit. So then ignition control unit actually applied it and do at 52 degrees before TDC ignition advance, right? So this is what actually happens in the engine. So it's actually mentioned here step by step. So once the signal is actually read, then this goes through an encoder into 8-bit digital form. So that's the binary value. It's a digital computer. So then it's not directly actually reading, it goes into and store in a register. Register means like memory location. Registers are memory locations in a computer. So these register, once it go to the register, now memory is actually having this particular number. So that means this is the number. So binary 32, yeah, it should be changed. So this particular number value should be here, right? Once it stored there, memory actually check all the lookup table until it find the similar code. So this one and find out the similar code. Okay, once the similar code is found out, memory until it issues another binary code such as this one. In this case, that's the one actually was available for this particular ignition advance. So then this particular code will be actually sent into the ignition timing module, right? Then it will be actually sent to the ignition control module. So ignition control module then set up 50 degrees before TDC. So this is what actually happens. So based on then ignition control system actually takes over and it's try to actually advance little by little in order to maintain the engine. So this is what actually read by the engine. So based on the airfoil ratio and as I told you earlier, airfoil ratio and all these other parameters also maintain in this or change in this. So based on that, then ignition control module can take an decision to actually change, advance or retard the ignition timing based on that. That's what we discussed previously. So all of these actually once you so wait. Yeah, so storing all these data has to be stored in somewhere, these registers. Once you stored everything, it's actually comes like a sounds like this sort of a table, right? This sort of a table. So these tables actually and values, these are actually values, but but these values are not exactly depends on one or two variables. Usually it has three variables. For example, ignition timing is actually based on the engine RPM as well as the engine load, right? It's based on both of them. So all of these things are interrelated. So once you actually filled all of these values, it's actually developed sort of like a surface area, right? Something like a map, right? So finding out these values, storing these values into the engine computer module or this engine control unit is actually known as engine mapping, right? So whenever a new engine is actually developed, so all of these things actually have to be mapped. So how it actually done is, or all these values has to be actually put into the engine. So how it actually done is, first they do a modeling, a computer control computer modeling of the engine in order to find out the rough or the basic map or basic timing, ignition and everything, right? There's softwares, there's so many softwares to do that. Then based on that, right, based on that, once they completely manufacture the proper prototype engine, use these values and uh, fix the engine into a engine dynamometer, then start mapping the engine and running continuously run the engine until you find out the best possible value, right? Best possible values, and keep running until the engine comes up to a full graph, right? Full complete graph that shows and explain that that actually performs very well. So each step of the way, the lookup tables are going to be updated and new data is going to be actually put in. So you might actually have heard something called like chip tuning and everything. So chip tuning and all of these things also doing the same thing actually. Basically the same thing, but there are small differences between the chip tuning and this mapping, but basically it's the same thing. Basically it's the same thing. Even this ECU tuning, chip tuning, standalone ECUs, all of these things are actually done. All of these are actually done for the same reason. So like standalone ECUs and everything are the ECUs that are available for anyone to purchase and fix to any engine or sort of thing. So we can have our own ECU, or we can actually program to our own liking. So most of the ECUs are coming in the vehicle itself from the manufacturers. They are not happy with changing these values or these changing these maps or these lookup tables. So in such cases, buying a separate ECU is possible. ECUs can be buy separately and fix it to actually reprogram, but it's going to cost a fortune. So the step by step of the way, the how the vehicle engine and everything is developed. First thing, as I told you earlier, mapping the engine. So first thing is to find out the values and map the engine, and using a dynamometer, right? Using a dynamometer. So afterwards, that after doing that, then that particular engine is going to be fit into a car. So based on the vehicle that's going to actually put into, oh, the dynamometer graph has to be changed a little bit in order to give the maximum drivability for the passenger, the drivability of the vehicle. So in order to have, take the maximum drivability. So once the base dynamometer graph is actually placed, this particular engine then put it into a vehicle and do the mapping again. So in this case, vehicle will be driven on a, we call this is as a chassis dynamometer, where you can actually drive the vehicle on while it's measuring the power and torque outputs, right? In addition to that, it's possible for these things to be actually running continuously according to a driving cycle. Driving cycle means uh, how do I say this? Standard driving. Uh, it's possible to actually develop like a small graph. Yeah, actually give out a outline of the driving characteristic of any country or area. Right, that's called a driving. cycle. So by using a driving cycle and a dynamometer, it's possible to actually uh, possible to drive the vehicle on it and make sure that the vehicle will perform, make sure that the vehicle's drivability will be better once you do that. So one advantage of doing this method is, so you have all the drive components, weight, all the components, the drive suspension and everything is fixed. So especially this transmission is fixed, so the resistance for the driving, the wheel weight and everything is fixed here. So it can be very well tuned, so engine can be very well tuned in order to uh, meet the necessities of the driver or the owner who's actually driving the vehicle. So once this part is done, then it's actually tested as a whole vehicle. So in this case, the engine performance and the vehicle overall performance, the how vehicle is going to perform, suspension, chassis, everything will be tested. While this is doing, also if there's any problems found in the engine, again it goes back to these two processes and change the maps. So sorry, these maps again, and until the manufacturer happy with the whole product. So once they do all of these things, then engine actual vehicle actually goes to like a real world testing. So this is the number 3 is actually done on like a proving ground, where the like vehicle testing tracks are there, and on the race tracks there's a different testing areas there, vehicle proving places. So this is actually done on so areas like that. Once this is actually finished, the whole vehicle will actually go on like a road trip sort of arrangements to actually check the vehicle's overall performance and how it's to behave in the traffic conditions, temperatures, various driving conditions, highways and everything. So when it's actually going on such a testing, the vehicle is actually covered in such a way similar to this. The whole idea of this is to not to show the whole body and what sort of vehicle is underneath. So this is just for marketing sort of things, so they don't want actually to show the vehicle before it's actually released. So that's how, that is what the basic development of this engine dynamometer. So that's one more reason. So as I told you earlier, sometimes the same engine, right, same engine in different vehicles have different power outputs, different driving characteristics, right, different characteristics of driving, because the mapping is different. So because these lookup tables values are different, how the engine actually perform is different, right, how the engine perform is somewhat different. Sometimes they even produce more power, same engine actually produce in some different ways, right. That's possible with these things, mainly due to this computer system that can be programmed. So once everything is actually done, once everything tested and done completely, you end up having something like this, right, something like this. So this is actually a complete engine map, right. So this is complete engine map. One is actually showing the first one is actually ignition map. So this one is ignition map, the one is also ignition, the one is a fuel map. So the black and white one is a ignition map, where the ignition is going to be, right. So engine speed, throttle opening and ignition angle, right. So as I told you earlier, it's very simple, it's later also explained. So graph means first, so one graph is actually drawn for, let's say, 0 degrees throttle. That means at idle, or how much, let's say, zero ignition, zero engine load, how much of throttle ignition angle has to be kept uh, for each RPM, right? This is the first graph. Then another graph, right? Another graph is drawn for, like, say, 10 degrees, uh, 10 degrees engine load, right? So now 10 degrees engine load. Next, I'm going to draw another graph for 20 degrees engine load, right? So now 20 degrees engine load. Another graph I'm going to draw for 40 degrees, right? So same RPMs, right? So we have the same RPM. So this is RPM, right? This side is the advanced. I'll put advanced, right? Then so each one of these axes, each of these graphs actually represent a engine load, right? Particular engine load. So this direction, you have engine loads, right? So once you combine all of these three axes, you ended up having a complete map similar to these, right? So again, I have engine load in one axis and RPM on the other axis, and I don't know whether you can see this. Yes, advancing another axis. So once you combine all of these three axes, once you combine all the points in surfaces or combine all the points, you ended up having a surface. That surface is actually known as the engine maps, right? So that's what engines map. So engine map, if it is having more reference points means each of these values. So here example, engine load, right? Engine load is actually in this point 0.27, 0.57, right? So this is the one. So if there's another point in between, right, let's say 0.35, if there's another point in between, right, that's a reference point, right? That's a reference point. So having more reference points means optimum operation is possible. So any point can be actually found by the engine. So otherwise what actually happens is, if the engine is not possible to find, for example here, right, if the engine is able to if engine found like let's say engine found the engine load is around 0.4, right, 0.40. So at that time engine actually have to decide whether it's close to the 0.57 or 0.27. So for whatever it's actually close to, it will actually select that particular one, find out the closest one, and based on that it's actually finding out the necessary of actions for, right? So having more reference points are actually better. So it's just that's what the engine map and how the engine map actually gives the readings and everything. But in order to get the readings from the map, first you need to actually develop a map. So how do you actually develop a map? Right, so map has something to do with airfoil ratios, the power and the torque, right? So for any vehicles to actually operate, right, any vehicle to operate in its optimum condition, there's a torque and power curve necessary, right? So the ideal torque and power curve, right? Ideal torque curve is something like this, right? So power is actually a product of torque. So engine actually produce torque. So that torque transferred into power, right? So that's why we only consider about the torque in this case. So torque, this is your torque, this is your RPM. This is the ideal torque curve, but it's impossible to get this torque curve. That's why we actually use a gearbox, which I will explain in your transmission module, transmission unit. So but the because of the design of the internal combustion engines or the reciprocating engines, the torque curve should be somewhat looks like this, right? While the power curve goes similar to this. But you have to understand, so these when the torque curve and power curves are actually changing, that actually affect how the engine is actually performing. So there's a possibility, it's possible to bring this torque. So the highest torque is actually received around 3500 rpm, while the highest power is received or reached around 5500 rpm. But it's possible to actually change by changing the fuel supply and ignition timing. These can be actually a little bit changed, right? So when if you know what sort of a vehicle and where you want to drive it, how sort of what sort of driving you are expected to do, based on that power and torque curve can be actually identified. From that torque and power curve, right, actually the torque curve, from the torque curve it's possible to actually find out spark advance or spark ignition, spark position versus torque graphs, right? And the fuel, how much of fuel has to be given to each position, right? So based on that, right? So this is your final goal. This graph is your final goal. So in order to find, bring this up to this final goal, how much of power has to be given, how much of fuel and ignition has to be given at each position, right? Based on the air coming in. That's how these actually graphs are developed. So for each and every position, once you develop the graphs, right? So you have sort of set of graphs. Once you combine all of these graphs uh, into sort of like a booklet, you ended up actually having the engine map automatically, as I explained previously. By combining different RPM ignition maps, you can actually get the total or complete map sort of thing, right? So the map or the fuel and everything is actually dictated by what power and what torque curves are necessary. While it's actually doing that, it actually always have to maintain these air fuel ratios and how it's actually going to affect the emissions of the engine, and how the emission and how the efficiency is actually going to affected by these things. So for a vehicle that's being used in day-to-day driving or daily driven vehicle, this is a big deal, that how much of fuel and how much is the efficiency and everything. But if it is like a race vehicle or something, nobody cares about how much is the emission, as long as it's making more and more power, right? So those sort of once you combine all of these, once you consider all of these things, can finally come up with the ignition map. So or the complete map for ignition, fuel and everything. So it's not easy as I'm saying here, but that's the basic process, right? So this mapping is necessary for the engine controlling. So mapping is actually done based on what are the characteristics necessary for that particular vehicle, right? So yeah, so sorry. Yeah, so this is actually a image actually showing a ROM or the stored data in one of the ECUs. So these 2D graphs is a cutway of a, so these 2D graphs are achieved by just taking a cut, taking a one cut. So if you do a cut in one place, you end up having a 2D graph like this, right? So that 2D graph is achieved like this, and the map table is responsible for actually developing this particular map, right? So this is how the engines are actually designed. So it actually gives each and every data. So what sort of RPM, what's the engine load, what's the ignition, so how much the engine temperature. If the engine temperature is not up to the correct limit, then how much of fuel has to be increased, so how much fuel has to be increased for how much longer until the fuel, when the fuel increased, okay, now fuel is increased, that means we have to actually retard the ignition timing. So all these small things has to be actually calculated, or not calculated, actually implemented while the engine is actually operating. So engine temperature sensor, oil pressure sensor, everything is actually fed into the computer system itself. So there are two important maps in a vehicle, or maps that used in the vehicle. This is not the only two maps, there are so many other maps, but two main important maps that we have time to discuss is the spark advance and the air fuel ratio. So air fuel ratio and fuel amount to air fuel ratio actually gives out how much of fuel has to be provided into the vehicle based on the engine speed and the engine load or throttle opening, right? So that provide how much of fuel is going into the engine. Once the fuel is sent, provided to the engine, the lambda sensor provided the feedback, okay, engine is not engine is doing well with the fuel, engine is not doing well with the fuel, or that means the engine is combustion process is good or not good. So if it is good, no problem, the fuel can be maintained. If it is not good, engine either have to engine actually have to reduce the fuel or change the fuel. So for example, if it is rich mixer, the fuel actually try to reduce the amount of fuel based on that. While this is actually happening, ignition system actually check whether the knocking is going on. If the knock is generated, uh, while the fuel is actually delivering, engine load and engine speed identifies, okay, this is the engine speed and this is the engine load, so ignition spark should be here. While this is actually happening, so ignition spark is given, now the fuel is combusted and the exhaust is coming up. So from the exhaust, engine identifies the fuel ratio is not up to the task, so fuel ratio has to be a little bit changed. So that sends to the engine control unit. From their engine control units informed it to the fuel control system. Fuel control system actually trims down the fuel. While this is happening, ignition system actually here ignition system actually listen to the knocking. If a knocking occurs because fuel reduction based on the feedback from the lambda sensor, ignition system now understand, okay, there's a knocking started, so we have to take action. So retard 1.5 degrees. So 1.5 degrees, the ignition spark will be actually retarded, right, until it's actually go away, until it's actually it's able to actually completely turn off the, or completely stop the knocking occurrence, right? So that's what basically happening here. So this process, the fuel ignition, the management of this complete system is done by the engine itself. Okay, so even though this is the usual method, but now little by little the companies such as Lucas are trying to adapt a new system which have the capability of actually adapting the ignition timing to the engine based on the vehicle scenario, operating scenarios, right? So it's actually, the reason being, even though the same car being driven on the same location at by different drivers, the different small differences uh, could actually change the performance of the vehicle and the efficiency of the vehicle. So adaptive ignition system, so which actually has the capability of adapting the ignition system to the scenario, is actually known as the adaptive ignition system, which actually has the ability to alter the um, spark timing very fast. So it's actually provide the ignition timing to be change very fast. It's actually a bit complicated than the previous method. As you can see, it actually goes through quite a bit of process before it's actually changed the ignition timing here. As you can see, there's few maps. So this is one map here, and fixed spark map and variation generator, spoke detector. So there's two maps included here, and there's a lot of electronic components. And finally, you have another timing correction map signal. So each one is giving one output from there, and the output just to find out the more suitable system. So these sort of things will be very common in the future. So that's the basics of the engine management, but the engine management is not done there. So one, as I told you earlier, engine management actually control the whole engine, as well as it has been developed up to controlling of the whole vehicle. So engine actually take care all the readings from every components of vehicle and controls provide output for actuators for actuator. One of the two examples we discuss is the fuel control and the ignition control, right? Fuel control and the ignition control. The other one is the idle control. As I told you earlier, when the engine is not actually up to the operating temperature, engine is actually operating at a higher operating RPM in order to bring the engine up to the operating temperature. In addition to that, when the engine is having additional load from the ignition system, from the air conditioning system and any other electronic components, and such cases also engine may need to increase the idle RPM. So that those sort of things actually done by using the idle control, which we discussed in the fuel systems. Right. In addition to that, there's so many chassis related components and the drivetrain related components, which we will be discussed once we finished the basics about the basics on the drivetrain and the chassis control module. When this is all of these things are actually happening, what you have to remember is for each and every system of the vehicle, there's a separate module inside the electronic control unit, also known as powertrain control module. So all these powertrain control modules, or all these modules actually have to be discussing or has to communicate with each other. So for communication, vehicles actually use a system called controlled area network. So as you can see on, there are two images. The first one in the black and white image, there's a one the chart A and chart B. So chart A is a normal system where each system has to be communicate with the separate wiring or separate circuit to go each for dedicated for each communication line. While the second one is actually showing a data bus where it's actually data is sent to all the modules, but only the necessary or only the relevant module will be actually taken the corrective action or whatever the signal comes in. So that's the second one is actually the CAN network. So it's actually by using this, it's actually provide the system to digitally communicate while reducing the necessity of communication lines. So it's only have two buses. So that two buses is enough to actually discuss and control the whole vehicle. So this is not actually happening outside of the issue. It's mainly for discussions or communications inside the engine, control modules, only for communication control modules. So so this data bus, there's a structure or the protocol is there. This protocol is dictated by which so each module has a separate code. Once the code if the each module find out the coming signal has a code, then only it will be actually considered in. So I'm not actually planning to go forward in these CAN networks and these vehicle control because that's a big module. Right? This is a huge area that if you are interested, you can learn further as well. So I'm just giving you, this is foundation in automobile technology. Just need to know this is the system that's communication is happening inside the vehicle. So inside the vehicle means inside the vehicle is actually a computer. It's nowadays it's a computer on wheels. So that communication is an important part. So next, I'd like to discuss a little bit about the maintenance and the fault diagnostic. Very simple part. Again, it's like a huge topic, so I'm just going to go through the basics again. So yeah, so one advantage of this engine management system is if there's any problem occurs, it's possible for it to actually identify. It's possible for it to identify. It's actually known as self-diagnostic capability of these engines, right? Self-diagnostic of these engines. So the self-diagnostic of these engines are uh, well, quite a bit important. This was actually introduced. This onboard diagnostic or self-diagnostic is actually introduced as a regulation, right? It was not done by the companies itself because it's going to cost a lot to include these things. Then this system was actually introduced, regulated by the governments to be put into the vehicles as a emission reduction method. So the idea here is, so if something wrong in the vehicle will be able to actually inform it to the driver. So there's something wrong. The emission system is not actually working well. So please take it to someone to take a look at, right? Take a look at. So so once engine actually found out any sort of issues are there, if the vehicle is still operational, some sensors and some modules are there, without them operating well, the engine can't actually perform at all. But there are some things still engine can operate without. In such case, like a small module, the engine will be actually able to run. For example, if it is like a throttle positioning sensor, engine can't actually run, right? Because engine don't know how much of load is actually put in the requested by the driver. But if it is not like that, if it is a simple problem at such a case, engine can actually still run. So and such situation, engine turn into something called a limp home mode, where it's actually provided limited operation until it reach to a maintenance place, right? Maintenance, or at least until you drive it to the home or garage or something like that. So this engine onboard diagnostic system is available in two methods. So basically there are two diagnostic. One is onboard diagnostic, other one is off-board diagnostic. Onboard diagnostic mainly concerns about the vehicles emission. So if anything related to emission happened, or anything goes wrong related to emission, at that time check engine lights comes up. It does not mean that the engine is actually broken. That you have to remember, right? Engine is having some trouble. That's all it means, right? But if it is if it is actually not like that, if it is having a bigger problem, that's actually comes under the off-board diagnostic. Off-board diagnostic means it's not related to the emission. Usually anything not related to emission actually comes under the off-board diagnostic. Off-board diagnostic. So on-board diagnostic, off-board diagnostic, the self-diagnostic technology was available in two methods. First one is ECU. Once the ECU found out sort of errors, it's actually stored these errors. Then stored errors can be either read within a dedicated computer, right, which is known as a DTC reader, the diagnostic trouble code reader, or you can just use a check engine light. Just use a check engine light, and by using how it's flash on and off, similar to the one image shown here, and finding out what is the problem of the vehicle, right? That is also possible. So this system, the one shown in the first image, is almost not in use at the moment because it's quite difficult, and there's a possibility of misdiagnosing, because as you can see, the light switching and switching off is actually having these gaps. Timing has to be measured properly, otherwise you will make a big mistake. So this is almost not used, but this DTC code reading system is very much available. So yeah, so I think onboard diagnostic system I already explained to you. So this previous system, as I told you earlier, I actually use this switching off and on the check engine light was how they actually communicated. But nowadays these codes can be read using a universal diagnostic code reader. So for each number, each letter and everything, there's a problem mentioned here. So in order to find out these things, you need the that particular computer to read these things. Once you come to the university, I can actually show you these things. We can actually have some, can actually do a small practical on this just to show you how this actually works. So this is the communication port. This is standard port. So every vehicle manufacturer has to have these in order to sell the vehicles. So it should be available within like 1 to 2 feet from the driver's seat. That's also a rule. Right, so with that, engine management system is over. Yeah, before I go ahead, so this how these things actually find out something is wrong. So very simple system is used. So as I told you earlier, all the possible scenarios are stored in the engine, right, in the computer or in the computer ROM. So if there's any values comes out of these readings, right, if something comes out of these readings, so for example, for engine, let's say engine RPM, you got engine load saying 100% and the engine RPM is 300. What you're reading is 300 engine RPM, but engine load is saying 100%. So that's not possible. So it's not possible. So at that particular time, engine actually have to put a recheck everything. While this is rechecking, it's actually storing this particular problem in the system, right, in the system. If it is actually fixed again, if it is fixed in the next cycle, then no problem. Okay, that was error, no worries, no check engine lights is coming on. But if this is going to continue again and again and again, right, if this cycle is going to continue for a few times, then engine understand, okay, this is wrong, something is wrong, it cannot find out this value. So that value is not available in your computer system. So that means there's a problem. So whatever the value is not available is where the problem should be, as per the what engine understands or the engine management system understands. But it does not mean that is the exact problem. So it actually gives a probable reason. So this area, this particular sensor is out. So for example, this 100% and the engine RPM is saying 300. So that 300 RPM could be wrong, because throttle positioning, every other values for any other throttle positioning or engine, any other engine loads, there's a value. So that means something wrong with the engine RPM reading. So then the engine RPM, check the engine RPM reading or something is wrong. That's what the code says. So that code, it does not mean you just have to replace the engine RPM reader or speed sensor right away. That no, that's not going to help anyway. And that's not going to help anyway. There are other steps you actually have to go through. So one of the main things is you actually have to check everything around it. So like power outputs, voltage inputs, voltage outputs, wirings and everything beforehand you actually replace. So this fault diagnostic, even though this onboard diagnostic is giving the possible scenario, possible part that went wrong, it's not giving 100% sure answer. There are some components interconnected. For example, ignition timing and the ignition timing, as well as fuel system, fuel timing. For both, actually you need the engine load and engine RPM. So for either one of these goes wrong, and engine trouble code may not actually give you the direct reason. It could actually give you some reason related to that, right? Some reason related to that. From that onward, you actually have to find out what is the proper problem. So to do that, you actually have to use proper fault diagnostic mechanisms. So there are like few steps you can use, sort of like we use like 6-step approach. There are some approaches like that, so which we'll be discussing further later on. But this particular unit or diagnostic reader could not directly give you the reason at all times. Sometimes it's actually right, but not all the time. So it has to be checked very well around it as well. So yeah, so that with that, I would like to actually end the engine management system. So there's so much details I included here for you guys to read, and there are few videos also included. And I might have some videos related to this engine dyno pulling and doing what do you call this, driving cycle testing. So I'll upload these. I'll send you the links for these videos. You can go ahead and watch them. I'll try to show these things in a practical situation where how these particular difference between these engine management systems and how each type of vehicles are using these things in the next week. Uh, yeah, with that, I would actually like to end the class. So if you have any questions, you know where to find me.